Alright, let's discuss Chapter 15, Displays and Image Processing. So, we should all know that the display is what we are going to see, where we are going to see the information from the patient. So it becomes this essential link between the system, the ultrasound system, and the entire medical staff, because we are the eyes of the radiologist. Today's systems utilize what's known as a flat panel display. These displays are built upon the old technology of television screens, but utilize modern digital modalities to do that. With that, you get higher frame rates and you get more lines per image. When I say higher frame rates, the televisions, as we know them, have a standard frame rate of 30 frames per second, which is actually very low. The lines per image was about 512 lines per image, and that was set standardized across the world at one point. Well, actually across the nation, the Western world. Europe used a different system called the PAL system that was slightly different. Anyhow, utilizing our flat panel displays, we're able to get frame rates in the hundreds, if not a couple hundred frames per second, and we can get lines per images. If you've heard of a 4K monitor, 4K television these days, it's 4,000 lines instead of 500. So that's a significant difference in image quality. We initially started with bistable images. These were where we were able to utilize two shades of gray, one shade being black, the other being white, and the bistable image could be represented by a single binary digit. And binary digits are the smallest component of a computer, and they can be either 0 or 1. What you're looking at is an ultrasound of a bistable image of a set of triplets. Yeah. Those, you can see three head up in the top of the image, an abdomen next to it, and then parts of another baby here. I'm not sure exactly which parts. So we were able to get triplets with this bistable imaging, or triplets. We were able to get black and white with bistable imaging, creating these kind of pictures. Well, these are useful for diagnostic purposes, but they certainly don't look good, and there's a lot of pathology that can be missed. So if you add more binary digits, you're able to start representing things instead of as just black and white. You can represent them as shades of gray. So the echo strength now can correspond to a particular shade of gray, and we can do differentiation of tissues because we're able to see these different shades of gray. So when we look at our display controls, we have controls known as contrast. These are on the display itself, not part of the ultrasound machine, but part of the display monitor. And the contrast will determine how many shades of gray are available. If you have low contrast, what we call low contrast, you have many shades of gray. In high contrast, you have fewer shades of gray at your disposal. Your decision of what you want to look at may be somewhere in between these. Brightness, of course, is determined by the brilliance of the displayed image. It can be either faint and dark or very bright, in what I would call an overgained control. So the display controls that are on your monitors need to be adjusted so that the image that you see in the ultrasound scan room matches the image that the radiologist or obstetrician sees in the reading room. They need to be the same. Scan converters are the next system control after the receiver. The receivers take the information from the transducer, convert it into an A mode scan, and then this is sent to the scan converter where it is then converted into the B mode image. Early scan converters utilized what we call two-dimensional mapping and were known as analog systems. These analog systems were very prone to flicker and poor image display. When we talk about analog, what we're doing is we're comparing the real world to a computerized digital world. In analog systems, there's no discrete measures of things. Things are always on a range of values. So instead of saying that something would be the fourth level of gray, we'd say it is somewhere, it is a high level of gray or a low, very bright pixel. Digital is computerized and only discrete values are allowed. So if you were saying that a pixel was an order of gray, you would then specify exactly what number was associated with that pixel, such as 254 if it was a very bright but not quite completely bright pixel. Analog scan converters, like most of the stuff that we've been learning about so far, are obsolete. This is an old B scanner with an analog scan unit. If you've ever seen an oscilloscope tracing in electrical components, that would be another version of an analog scan converter. Here is an image of an oscilloscope with a tracing across the middle here. So this is an example of an analog scan converter. The signal would come into it and it would be placed on a grid. And you can do this with grayscale, though this oscilloscope here is not a grayscale scan converter. Digital scan converters are able to take the A mode signal and convert it directly into numbers, which will then be displayed by our monitors. These numbers are then stored into computer memory as a series of zeros and ones, which are binary digits. The computer then translates the stored data into an image. And so we just let the computer do it. Now this on an ultrasound machine is absolutely no different than the display of that is done with any other computer that you may have used in your life. So every computer that we utilize uses a scan converter of some kind. The advantage of digital scan converters is you get very uniform images. The images are very stable because they're not relying on a signal coming in. They're relying on stored information in the computer. These digital scan converters don't get affected by heavy use or aging. The speed is much improved over the analog variety, and there's fewer errors, so there's absolutely no reason to use an analog scan converter. This is okay. So more on digital scan converters. There's two elements of the digital scan converter that are important for you to understand, and that is the number of pixels and the number of bits. The number of pixels is how many points across the scanned image that we can see. So a pixel is a picture element. It is the smallest point of a digital picture. And at any point in time, then this will be assigned a shade of gray. The more pixels you have, the better your spatial resolution. So we see here this lion or tiger on the left, or lion I guess it is. And then on the right you can definitely see the better resolution of this beast with more pixels. Pixel density, on the other hand, is how many pixels there is per inch. And so we want a high number of pixel density anytime we're looking at images. Here we go. The pixels, the fewer pixels per inch, the lower your density, your image density. More pixels per inch, the higher the image density. When you have low pixel density, each pixel itself is larger and you get less image detail. When you have a higher pixel density, you get smaller pixels and more detailed images. And what goes along with the pixels is the bits, and this is the binary digits. So bits in a general term is a binary digit. It's the smallest amount of computer memory available. It has a value of either 1 or 0. And typically bits are grouped together in groups of 8, which we call bytes. Okay, so a group of 8 bits is a byte. Now you should be fairly used to decimal numbers where you have 10 choices of 0 through 9. With bits, the computer only has 2 choices, 0 or 1. And that is because in the computer, a bit is stored as either no voltage or voltage. So there's either 0 volts, or if it's a turned on bit and it's a 1, it generally will have 5 volts, and these are controlled by transistors. So when you hear about computers being able to have millions or billions of transistors, this is what they're able to do with them, is they make bits out of the transistors. As we said, bits are stored in groups, generally a group of 8 bits, which we call a byte. You can have groups of more, such as a word, which is a group of 2 bytes, a double word of 4 bytes, or 32 bits, or sometimes computer scientists will talk about a nibble, which is 4 bits. Okay. We don't really have to worry about any grouping of bits other than maybe a byte or a word. That's pretty much all we ever get into. The thing about a bit is, especially when you're looking at a byte of information, the grayscale of the image is determined by the value of the byte associated with the pixel. So each pixel shade is determined by the value of the binary bits associated with the pixel. Now, for each pixel, the more bits you have, the more shades of gray you can have. So, as an example, if we only had 2 bits for each pixel, we would be allowed to have 4 shades of gray, because there's 4 combinations that can be made with 2 bits. So imagine 2 bits, they can either be 0, 0, you can turn one on and have a combination of 0, 1, you could turn that off and turn the other one on and have a combination of 1, 0, or they could both be turned on and you'd have a combination of 1, 1. So this is a situation where you'd have 2 bits allowing 4 shades of gray. And your shades of gray could be anything, but let's just say they're black, white, light gray, dark gray. Okay, now if we put additional bits of information assigned to each pixel, we can have more combinations of gray. So if you have 3 bits, now you can have 8 combinations of gray. If you have 4 bits, you could have 16 combinations, and 5 bits would give you 32 combinations. So a byte of information, or 8 bits, would allow up to 256 shades of gray. And that's a pretty significant number. So 256 shades of gray would be 8 bits associated with the pixel. Okay. So some of the questions you may see on the SPI exam is how many shades of gray can be displayed with 6 bits of memory? And the answer to that is always going to be 2 to the raised to the power, to the number of bits. Okay, 2 to the number of bits, or 2 to the n, where n is the number of bits. So how many shades of gray can be displayed with 6 bits of memory? 64 shades of gray. Another way you can do this, if you can't remember to do the 2 to the number of bits, is just multiply 2 by the number of bits. Okay, so if there's 8 bits, that's 2 times itself 8 times. Okay, so I said that wrong initially. You don't multiply 2 times the number of bits, you multiply 2 times itself the number of times that you have bits. So again, if you have 2 bits, you're multiplying 2 times 2 and you have 4 combinations. If you have 6 bits, you multiply 2 times 2 times 2 times 2 times 2 times 2, and it gives you 64. So that's how we determine how much memory we're going to give to our grayscale image, is how many shades of gray we want it to have. So in these pictures on the left, we have very few shades of gray. It's high contrast. We don't need so many bits. On the right, we have many shades of gray, and it becomes what we call a low contrast image. Okay. Analog and digital image data, echoes received from the transducer are inherently analog because they can be of any size, and then generally either at the transducer or farther along the system they become converted into digital form. And so instead of saying a weak signal or a strong signal, we give that signal that comes to the transducer an actual number. We could measure the voltage and say it has 8 microvolts. Okay, and then we would store in the computer, we'd say, okay, that has 8 microvolts of power, so for that echo that came back, that's the amount of strength it has. And some other echo comes back and it might have 10 millivolts or something. But at any rate, this information as it gets to the transducer is analog information, and then it is sent to the receiver either as remaining as analog information, or in the case of newer machines, and when I say newer, within the last 10 years, the signal is transferred at the transducer itself into a digital signal and then sent to the receiver. So at some point though, the analog information from the transducer is converted into digital information that is used by the computer. We call that an analog to digital conversion, okay? Or analog to digital converter is the part of the system that does that. I already covered this slide. In binary, so when we talk about analog to digital conversions, we also have to think about binary to decimal conversions, because the computers do this too. So if we're saying that we have 64 shades of gray, we have to know how to convert that 64 into a binary number. So there's a lot of ways to do that, and there's a lot of books that will teach you that you multiply the digit along the byte times 2 to whatever nth power it has, from going from right to left along the number line, so that you start with 2 to the 0 times, in this case 1, 2 to the 1 times 0. That's a very, very difficult way of trying to remember how to do binary to decimal conversion. So I'm going to show you an easier way, and hopefully this will work for you. So the easy way is you take your digital number and you just write it out. 1 0 1 1 0 1 0, 1. Then the next step is to put above it a converter, what I call a decimal converter. And we start with the smallest possible number that we can double, and we start doubling it. So don't start with 0 because you can't double 0. 0 doubled is still 0. So we start with 1, double it, we put a 2, we double it, we put a 4, we double it, we put an 8, we double it, we put a 16, doubled 32, doubled 64, doubled 128. And so we've just ran out of our binary number, and we don't have to put any more. Now, every place where you have a 1 underneath your converter table, you write the number down. Okay, so I have a 1 under my 128, so I write down 128. I have nothing under my 64, so I move on. I have a 1 under my 32, and also I'll write down my 32. I'm going to do the same for the 16, the 4, and the 1. All I have to do now is add these up. It's that simple. So the binary number 1010101 converts to decimal as 181. Okay, so that's very simple to do. Anybody can do that. Now let's go from decimal to binary. So from decimal to binary, you want to start out by writing out the number to be converted to binary. For example, 329. Okay, so we're going to write 329 down, and then we're going to create a conversion table up to the number to be converted. So again, my conversion starts with 1, I double it to 2, double to 4, double to 8, 16, 32, 64, 128, 256. If I double 256, I'll end up with 512, and I don't need 512 because my number is 329. So what I'm going to do is I'm going to stop here at 256. Alright, now the next step is to write a 1 underneath the 256 and then subtract 256 from 329. Okay, and so then we get 73. Okay, so we use the 256, so we put a 1 under it. Now we cannot subtract 128 from 73, so we're going to put a 0 there. Alright, but we can subtract 64 from 73, so we're going to put a 1 under the 64, do the subtraction, we're left with 9. And so now we look at what we have left. Okay, we can't subtract 32, we cannot subtract 16 from 9, but we can subtract 8 from 9, so our next step is going to be to put a 1 under the 8, and that leaves us with 1. Well, we can't subtract 4 from 1, we can't subtract 2 from 1, but we can certainly subtract 1 from 1. Okay, so that leaves us with 0, and that gives us our binary representation of the number 329, which is 101001001. There you go. So it's not difficult, there's a few steps involved, but it's actually very easy to do. You should practice these because they do tend to show up. Now let's talk about pre- and post-processing. So on today's machines, pre-processing is any processing of the signal that takes place while the screen is still active and we're actually doing scanning. Post-processing is anything that you can do to the image after you've hit the freeze button. That makes it simple. Now, in the old days, and you may see questions like this, they considered pre- and post-processing. The pre-processing was the signal before it got to the scan converter, and post-processing was the signal after the scan converter. So the scan converter was in the middle of the system, so to speak. Today, that's no longer true. We can do a lot of our pre- and post-processing on things that are before and after the scan converter. Alright, and the scan converter is not at any particular spot anymore in our systems. Let's talk about a process known as the zoom. Okay, Zoom is, as you would imagine, just enlarging the picture in order to look at a section of it. Now, if we do that on a frozen image, we're going to call that a read zoom. This enlarges the image stored in system memory. There's no extra information acquired. The image is just simply made bigger. May not be better, just simply made bigger. And I like to think of it as a book, okay? You can read a book, but you can't change the words in the book, all right? The book is just what it is. Right zoom, on the other hand, is when we select a section of our anatomy and we are going to enlarge it utilizing ultrasound. And so we use right zoom and we start sending pulses into that area, and we rescan the area and obtain new information and display it larger. Okay, so that's a right zoom. If you're the author of a book and you're writing a book, you can add to whatever information you want. So you can add to a book if you're the author. So that's right zoom. So read zoom, the book is written, we just make it bigger. Right zoom, we can add what we want into the book and make it bigger. Okay, let's talk about a process known as coded excitation. I think I mentioned this earlier in another lecture, but let's talk about it. Coded excitation requires longer pulses than normal excitation, but these pulses have binary information encoded into them. So this relies on the computer to generate these pulses. They're going to end up having a variable spatial pulse length, so our axial resolution may vary slightly, and there's multiple frequencies built into the pulse when we do this. So coded excitation, though, is a really nice feature. What we have is we can say that we have binary coded information in our transmit signal, so that these transmit signals go into the body, and then what comes back from the body we can discriminate when it comes in. So we're going to just talk a little bit here about what this means. And coded excitation is also known as chirp frequencies. Okay, so if you see that term chirp frequencies, remember this is just binary coded of the transmitted pulse, and also known as Golay coding. Now, Golay coding is a slightly specialized type of binary coded excitation which requires 2 pulses, but nobody cares about that. So Golay coding, chirp frequencies, and binary coded excitation are essentially the same thing. This allows discrimination of returned echoes. Okay. So this improves our signal to noise ratios and allows for something called B-flow imaging on the GE systems. And so I'll show you what that is in the lab. Let's try to do that I'll try to do that this week if I can remember it. Alright, so let me draw a picture and show you how this discrimination of return signals works to improve our signal to noise ratio. Alright, so if we let's say we're trying to image an area here. Alright, we'll just use a curvilinear array probe, and we're going to send out a pulse along this scan line here. Okay, and along this scan line we're going to get echoes back, right? Makes sense. Well, what happens if that pulse keeps on going down into the body, and then we get an echo back from down here? Okay, so we listen, our PRP is set to listen until we get to this level here, right there, But this echo that is down here is going to return later, and so it's actually going to get to our transducer as if it was coming from a structure up here. So instead of being a structure down here, it's going to get to the transducer as if it was in the next scan line from a structure here. Okay, and so then it's going to keep returning to the probe and give us a false image at this point. Now, this is the beauty of binary encoded excitation, is that on this line, the first line that we send out, okay, if we encode that with the code 1010, and then we encode this second line here with binary encoded 1001, when this echo here comes back to us, remember it came from the first pulse, the 1010 pulse, and so the binary information in it is going to be not equal to 1001, but it's going to be 1010, and the machine will see that difference and throw out this echo and not even display it for us. Okay, so that's how binary encoded transmission allows us to improve our digital signal. Excuse me, I said digital signal. What I meant was signal to noise ratio. Our signal to noise ratio is improved by utilizing this binary coded excitation. And you don't need to know about GE's B-Flow for the SPI exam, because that's a manufacturer specific setting, and so it won't show up on the exam. Let's talk about a new technique known as spatial compounding. And so this is a method of sending multiple pulses out at different angles to obtain echoes from reflectors at different angles. So how does that look? Well, with spatial compounding, we see with no compounding, the echoes all go straight down from our transducer, and of course some of them come back to the transducer, some of them won't. With spatial compounding, what we're doing is we're sending our pulses straight down and also at angles, okay, and so we're effectively being able to strike specular reflectors at 90 degrees from multiple points. Okay, so that's what spatial compounding is. So we send out multiple echoes, and we're able to compound these together or average them together to improve our image. So here is what a straight line being fired down is. Here's one being fired at 3 different angles, and then here's one at 7, and here's at 9. Okay, and then if we look at that over an area, it gets spread out even more. So basically it's a way of saturating the image with multiple pulses, and so this averages it. And with conventional imaging, we're left with less detail when we're striking small reflectors than we are with the spatial compounding. And if you look carefully at this, maybe on this example down here it looks a little bit clearer than this one. Honestly, there's not a lot of difference in these images. You can see they've got their focus right between these two phantom tubes here, so it's kind of hard to say exactly how the improvement has helped it. But it does help it a lot. You can play around with it in the lab and check it out, and you'll see that it does help you. One of the problems, though, with spatial compounding is that because we're coming in at angles, with true cysts in the body, we should see enhancement behind them, but these angles may not show the cyst because of the spatial compounding. So both shadowing and enhancement tend to go away with spatial compounding, and that certainly can affect your diagnosis. So be sure before you call something a cyst, or you say it doesn't enhance, that you make sure you turn off your spatial compounding, and so that you're absolutely certain that it does or does not enhance or attenuate. This is especially true in small gallstones. Many people have seen small gallstones these days and they go, oh, it doesn't shadow, therefore it could be a tumor. And instead they should turn off the spatial compounding and they'll see the shadowing. Another good place to miss a shadowing structure is in a kidney stone. And so this is something else that needs to be addressed by the sonographer during the scan. Frequency compounding is the same as dynamic transmit frequency. This is a method to reduce the speckle artifact. What frequency compounding does is that when we send out a signal, the portions of the display that are in the near field utilize the highest frequency component of our bandwidth, and the portions that are in the far field utilize the lowest components of our bandwidth, and so that we are able to get high resolution in the near field and good penetration in the far field using this idea of frequency compounding. This is dynamic transmit frequency, which means that it's done automatically by the machine and we don't have to worry about it. Okay, but it does allow us to utilize the entire bandwidth for imaging. Speckle, so I said this reduces the speckle artifact. I want to introduce you to what the speckle artifact is. So speckle artifact are interference patterns from reflectors that are smaller than the sound wave. So if anyone asks you what is speckle, you can say, well, that's just interference patterns from reflectors that are smaller than the sound wave. Another technique that is used to make things look prettier is edge enhancement. Most of your machines will have a button called edge enhancement. However, the Siemens does not. It has a button called C-Clear. Okay, basically the same thing. So anyhow, edge enhancement is a process that increases the contrast at edge boundaries. All right. So when we're looking at edge boundaries, we see improved contrast at the edge. Okay. It doesn't necessarily improve our image much more, but it's a way of seeing edges slightly better. Can be useful. Temporal compounding is also known as persistence, and this was on last year's SPI exam for sure. It utilizes temporal averaging, and so what it does is it takes a frame of information and averages it with the next frame that it takes, and then that'll be averaged with the one after it. Okay, so this is superimposing multiple frames over each other. And what it does is it improves our signal-to-noise ratio. If you want to know how much it improves the signal-to-noise ratio, each time you double the number of frames, it improves the signal-to-noise ratio by the square root of the number of frames. So, and the signal-to-noise is improved to the square root of n. Do you need to know that? No, you do not. But as an example, if we wanted to reduce our signal-to-noise ratio by a half, we would have to utilize 4 frames averaged together to reduce it by a half, because the square root of 4 is 2, and that would be halving it. If you wanted to reduce it to a fourth of what it initially was, you'd have to utilize 16 frames averaged together to reduce your noise by a fourth, to a fourth. The reason I'm making sure to point this out to you is that temporal compounding requires a significant amount of time to get a small improvement in signal to noise ratio. Okay, so having to increase our images by 16 times in order to reduce our noise by a factor to a factor of 1/4 is a significant temporal process. Let's talk about a mathematical technique called interpolation. Interpolation is the insertion of an intermediate value or term into a series by estimating or calculating it from surrounding known values. And so the picture on the left here uses no interpolation. So if there's information missing, it simply does not place it on the screen. The image on the right uses interpolation, so if there's an area which is missing information, it will average the pixel values around it to fill in that information. And you can see that the picture on the right looks significantly better than the one on the left. And interpolation, though, is not an increase in the number of scan lines. It's just simply a mathematical technique to make the number of scan lines appear as if it's got higher line density. So it doesn't affect your temporal resolution. In fact, it makes it very good. Elastography is a technique whereby we can apply a force to a tissue and see how much that tissue deforms. And the force is, of course, there's several ways we can apply a force, but that deformation of the tissue is known as the strain of the tissue. So elastography is also known as strain elastograms, also known as ultrasound elastograms, and more commonly called elastography. The imaging information is related to the mechanical properties of the tissues. So let's take a look here. If you have tissues in a very compressed state or tissues in a relaxed state, they'll look a little different. So here we see some jello, and we're deforming the jello with a spoon. Okay, and you can see how the easily deformable jello is deformed throughout the image, but the almond that happens to be in the jello is not deformed whatsoever. The almond does not strain as much as the jello. Okay, so the spoon is applying the force, and what we measure then is the strain, the deformation of all the tissues. And what we find is that the jello deforms a lot and the almond deforms very little, and we can say therefore that the almond is hard compared to the soft jello. Okay, seems very simple with jello and almonds, but when we're talking about tumors, it's a little more important. So if we have stiff tissue and soft tissue and stiff tissue, when we put deformation, we get the highest strain in the soft tissue. Okay, so that's the basic principle behind elastography. Now let's take a look at an actual elastogram. And in this case, this is an elastogram utilizing manual compression, where the probe itself is pushing down on the tissues, and we see the areas that are in blue are deforming more than the areas in red. Okay, and that tells us some more information about the characteristics of the different tissues. Okay, so the red tissue is harder than the blue tissue. Alright, so now let's look at a more modern example of that. This is a breast tumor on a 55-year-old woman. So this was a very concerning breast lesion. It's taller than wide, so that's usually not a good sign for breast lesions. And it is has what appear to be spiculations off of it. So two very bad signs for breast tissue. So we applied elastography, and we can see that in this case the hard parts are denoted as blue and the soft as red, and this tumor is very much blue, which means it is very much hard. Now the thing about tumors or growths in the body is that benign structures tend to be soft and malignant structures tend to be hard. So this area shows a very hard tumor. And another thing that I want you to take away from this picture of the tumor is that when you look at it on grayscale, we believe that this dark area is the extent of the tumor. When we look at it on elastography, look how far out in these areas this tumor extends. So it suddenly extends much, much farther out than it did before. And they have found that elastography is very well correlated to actual pathology specimens as far as denoting the size and shape of the tumors. So it is very good. This is definitely the grayscale is underestimating the size of the tumor. Elastography is showing you the size of the tumor, and then over here we see the pathological specimen of this very same tumor. So here is another example of an elastogram. This is probably a fibroma in a woman's breast, and you can see that on the elastogram scale it's blue or dark blue, very, very soft and squishy. Okay, if we look at a very similar appearing lesion on the right here, it is not squishy. In fact, under elastography you can start seeing some spiculations, which are worrisome for cancers. And so this would immediately go from a BI-RADS 1 or 2, which is on the left here, to a BI-RADS 5. So that's a significant change in the diagnosis. Okay, and this was a tumor, breast tumor. All right, moving on to other display modalities. PACS and DICOM. So PACS is our method of storing pictures for long-term storage in medical situations. And PACS is what everyone uses today. We don't use film hardly at all anymore. I don't know of any hospitals or imaging centers that are using film that are not owned by old people that don't want to upgrade. The advantage to PACS and DICOM is that we have immediate access to images. The data doesn't degrade over time. The disadvantages is the initial cost, which is why Dr. M might not upgrade his system, because he doesn't want to incur that cost if he's going to be retiring in a year. But the other disadvantage is that the capacity is limited by the storage size. However, with modern hard drive capacities, this is much less of a problem. I think I just saw a 16 terabyte hard drive for $200 the other day. That's an incredible amount of storage. No reason why anyone can't afford that. I should say anybody with a PACS system. DICOM, on the other hand, is not the picture storage, but it is the protocol or the language that systems talk to each other. Okay, so DICOM is the language of the imaging department's computers. And CT can talk to an MRI, can talk to an ultrasound, utilizing a DICOM format, okay, or a DICOM protocol. So PACS is where the pictures are stored, and they get there by DICOM. So DICOM comes in, talks to your system, and collects the information and sends it to PACS. On PACS, all the DICOM information is then stored. Different types of recording and archiving techniques have been used over the years. We still have some paper media that is utilized on some of our systems. This includes the printed thermal paper that a lot of people, that's what they get when they do their obstetrical ultrasound. You give mom a picture using your thermal printer. So paper media is very common. It's very portable. It's easy to tear off that picture and hand it to mom and say, oh, look, there's your baby. But the disadvantage, if you're storing large amounts of it, it's bulky. It's difficult to make copies of it that are clean and good. And it can't display dynamic images. You can't have cine loops on paper. Another type of media is magnetic media. These are like computer disks, computer memory, magnetic videotape. These are all types of magnetic media, and they can store relatively large amounts of information. But if they get exposed to a large, strong magnetic field, it can completely erase all the information. So that would be bad. For years we utilized film and photographs to store our information. The advantage to this is we were able to get very high resolution images. We can do it in color, but it's bulky and it does require chemical processing. So that's a technique that no longer do we have to teach you. And it can also, you can impart artifacts from dirt or chemical contamination because of the processing. Optical media is has been used, and these are laser discs or compact discs. This is typically what PACS uses. You can store large amounts of data. It's inexpensive. It cannot be erased by magnets. Usually we utilize DICOM to store the information. But this requires its own display system. So if you've ever taken a DICOM file set and tried to display it on a PC, you'll quickly find that a normal PC will not display DICOM information. So there are many, unfortunately, many non-standard formats for display and storage, which I have some optical media for old GE Logic. They weren't even Logic, they were L100 systems, and I can't display that information because it's all on optical media that is non-standard. So that's a problem. Alright, so this concludes our chapter 15. I hope you found it useful, and we'll take a look at some other stuff at another time.